Hello medical students. In this video we will begin chapter 2 of our MCAT prep course, and we're talking about some mechanical topics: torque, equilibrium, and energy conservation. Now, this first section here is just the introduction, and it basically just gives you a brief overview of what's in the rest of the chapter, so there's no need to say anything else specific about this. So moving on to torque. Torque is a twisting quantity. So this is torque. We call it a twisting quantity, or a quantity that changes rotational motion. Now, it's not exactly a force. It's related to a force, but it's a little bit more subtle than that. So I wouldn't quite say it's a twisting force. I'll say it's a twisting quantity, and I'll explain here how it differs from a force and how it's related to a force. So when you twist something, if you twist it hard enough, it will rotate. And so that's how the twisting idea here is related to the rotational motion here. Another word that's often used in this context is angular motion. And the idea is that if I have, say I have a flat surface here, and then say I have a board that I'm lifting up at an angle. So say I'm applying a force up like this, and the other end of the board is staying still. Well, there's an angle here as I'm lifting it up. And so as it rotates, so as it's rotating around like this because of the force, that angle is increasing. So this twisting, rotational, and angular motion, these are all ways of describing the same thing, essentially synonyms. Now, I have written over here a diagram of some quantities that contribute to the definition of torque, or that are involved in the idea of torque. And here's an equation that tells you how to figure out what the torque is in terms of these quantities. So I'm going to leave this diagram here, but I'm going to redraw some stuff in a little bit more detail. So the idea is that you have a stationary point, and this, you can think about a lever in the context of a lever, then this would be called the fulcrum of the lever. And a medical example of this is joints. And here I've drawn the biceps. This is used as a example a little bit later in the chapter. And so here the fulcrum of the lever is there where the humerus attaches in the elbow to the radius and the ulna. So the point is that so as you're moving your arm, the elbow is staying constant in a constant location, and this lever, the forearm, is moving. So you could think of this as the elbow, for example, and then you have the lever arm. So this is lever arm. And this is what's going to move. Now, when I was doing the example of the biceps, the motion of the elbow, I was having the lever move up because the biceps is pulling it up. Here, this picture I'm going to draw as I've drawn here, the force is going downward. So you could either contort yourself in some way to show that, or you could just think of it as a different kind of system. Now, the way this is drawn in the book is you have this distance here, r. Now, this is really a vector, but vectors and scalars, the differences are sometimes sort of slurred over in there in the sense that it's not clear whether you're talking about a vector quantity or a scalar, which is the magnitude of that vector quantity. In any case, you can think of this r either as the distance from the fulcrum to the end of the lever arm, or as a vector that points from the fulcrum to the end of the lever arm. And then the picture has a force applied here. It's drawn like this, and then there's this angle here, which is theta. Now, I've drawn it a little bit differently over here, and the reason why is because you ordinarily think of the application point of a force as being where you draw the beginning of the vector that represents the force, not where you draw the end of the vector. So that might be confusing. You might think, well, am I applying a force up here? No, you're applying a force here, and I'm not sure why the diagram is drawn that way, but this is maybe a little bit less confusing. It could be because when you draw it this way, you can think of the angle without extending out this horizontal line this way. See how I've drawn this dashed line here? To draw the relevant angle in there, I have to extend that line out to show it's this angle that goes up from here to here. Now, of course, I could extend this line down this way, and I could extend this line out this way. And you see this angle is the same as this. You may remember from geometry that what they call vertical angles are equal. So by vertical angles, they would mean an angle, and then if you have two lines crossing each other at the angle, and then the angle right across from it, that's what they call vertical angles in that context. But in any case here, you can draw it either way, but the point is the force is actually being applied at this point. And that's why I've written here, the force is applied to this point here, and so force is going downward like that. Now, torque, and so then once we have this diagram here, we can write the equation for torque. We have all of the quantities there that are necessary, and so we write the torque is equal to F, the size of the force, the size of the lever arm, and then the sine of the angle. Now, this letter here is Greek letter, and it's called tau. So that's like the Greek version of a T, a lowercase t. So that's why it's used for torque. Torque starts with T. So tau is for torque. That's what this is called. Now, one more thing I want to point out, and I've written it, I've emphasized it in this diagram here, is that in order to make a meaningful statement about torque, you have to specify what the fulcrum is. So you have to tell, it's not just that there's a certain amount of torque and that's all there is to it. It's a torque about a certain point. Because, if I drew another point, say, I draw a point over here, for instance, well, then the distance from that point, if I was thinking of that as the fulcrum, would be different. And so that would be a different R here, and the torque would be different. So I could think of, I could think of this whole thing as a balance, and I could draw the fulcrum here, or I could draw the fulcrum here. And the point is, it's going to make a difference where I draw that fulcrum. That's important, and that's how the R comes in. So what the R is it's the lever arm, and the lever arm by definition is the distance from the fulcrum to where the force is applied. So that kind of goes into a little bit more detail about what this diagram looks like. Now, the book tells you that torque is a vector, and it is a vector quantity, and then they proceed to tell you that it's okay to think about torque as either going clockwise or counterclockwise for the purposes of the MCAT. Now, the reason why is because the MCAT's only going to do two-dimensional sort of pictures here where something's rotating just in a plane. And so what really happens, and so this is in three-dimensional space, what you would have is so I'm going to draw, so this is supposed to be a circle, and you're supposed to be looking at it from an angle. So this is like a flat plane, and it has a circle in it, and I'm going to have a fulcrum here, and I'm going to have a radius vector here, and then I'm going to apply the force going, along this circle here. So you should think of this as a flat plane, and there's a circle here, and there's a radius vector that goes like that. In this context, the torque would be a vector that goes up out of the plane. So this here is in the plane. And so this is the more sophisticated description of torque, and this is it's a vector, it's what's called a vector cross product, R cross F, where these are vectors. So it is a vector, but we don't really need to think about it as a vector in this context. We can just think about it, the size of it, as the size of the force, the size of the lever arm, the sine of the angle at which the force is applied. Okay. So now there's a special case, and I'll just erase part of this. There's a special case which often occurs, and this is sort of a simplified case. Let me try to draw this a little bit more accurately. And this is when the force is coming straight down. That's how the book would draw it. I guess I would prefer to draw it like this, because this is where the force is applied and it's going straight down. And so if I extend this line out and I extend this line here, well, this, I could call the angle this one or this one. It's the same angle, but in any case, it's 90 degrees. And so this is when the angle is 90 degrees, or if you like, pi over 2 radians, if you prefer radians, which you really should. So in this case, sine of 90 degrees is just 1. Now, remember, why is that the case? If I have say I have a right triangle that looks like this. Now, remember the sine is the opposite over the hypotenuse. Well, is this angle here, so this is theta, as this angle is getting closer and closer to 90 degrees, say I draw it to where it's like this, where the angle there is very nearly 90 degrees. The opposite is very nearly the same size as the hypotenuse. And so the opposite over the hypotenuse, which is the sine, is very close to 1. So when it gets to 90 degrees, the sine of that angle is exactly 1. And in that case, a 1 goes here, and the sine, so the sine essentially just goes away. It just becomes a 1, and you're just left with F and R. So in this case, torque equals F times R. The book, I think at one point says F times L, where it's calling L the length of that lever arm there. And you can, of course, call it whatever letter you want to call it. Here I've called it R, so I'm just continuing to call it R there. Now I want to briefly revisit the idea of lever arms and torque in the context of biomechanics. And a good example, well, this is still torque, so I shouldn't have erased that. A prototypical example is the biceps. So with the biceps, you have the tension in the biceps is going to pull the forearm up. So it's exerting a force on the forearm there, and it's pulling it up. Now, when you draw this, so let me try to draw a bigger picture here. So here you have the humerus. I'm not going to succeed in drawing this like medically accurately, but you've got, and then the radius. I think the small one is the radius, and the big one is the ulna. I forget, or the bigger one, and then there would be the wrist. Well, here, so here's the fulcrum. And then what the biceps, you could draw the biceps like this. But the point is that the biceps, what the lever arm is it's quite short. It's that distance. if you can even see your biceps, if you're in good enough shape to, see your biceps, you can sort of see that the distance between your elbow, the rotational point there, and the point where the biceps inserts, it's very short. It's actually a very short distance. Now, what this means is in order to lift something, so that what the biceps is doing, this is the force exerted by the biceps. To get enough torque to lift up something, like if you're lifting a dumbbell or something, the force in the bicep has to be very large. The tension, so that's the tension in the muscle itself. The tension in the muscle is generally going to be much greater, hundreds of pounds, much greater than the weight of the thing that you're lifting. Because the thing you're lifting at the other end, the torque that it's exerting, pressing down this way, it has a much longer lever arm. The distance from there out to there is much longer. So the force the biceps exerts has to be correspondingly larger to make up for the larger lever arm of the object that's pulling down on it. So it's surprising. You can actually look up if you don't already know. I mean, most of you probably know this like the back of your hand, but if you look up the amount of force that the skeletal muscles are able to actually exert, the local amount of force that they're able to exert, it's, if somebody ruptures their Achilles tendon or something, or their quadriceps tendon or whatever, then it can be, you hear it pop. It's like an explosive sort of event because there's so much force in there. So that's all we'll say about torque. Well, it's not, but it is for the time being. We're going to do a problem with torque later. Now let's move on to equilibrium. So the idea of equilibrium is balance. So this is balance. And it's a balance of forces, and I could say and torques. I really should say and torques here. Because the idea of equilibrium is the translational motion. So translational motion means an entire object. Like if I take this marker, the entire object moving along, the translational motion doesn't change, and the rotational motion, if it has rotational motion, the rotational motion doesn't change either. So that's what equilibrium would mean. Now, it doesn't mean that the object is stationary or that the object doesn't rotate. And I've shown two examples over here. Static equilibrium, where I have a mass on the surface of the Earth, and the gravitational force of the Earth pulls it down, but then the surface of the Earth pushes up with a normal force, and those two cancel each other, so it doesn't move. The two forces are canceling each other out, and so that's what's called static equilibrium. It's static because it doesn't move. It means a static, it's in stasis. And then an example of dynamic or dynamical equilibrium would be if somebody jumps out of a plane in a parachute and they reach terminal velocity. Now this is when the wind resistance pushing up on the parachute is equal to the force of gravity pulling down on the system. And so here, the person's moving but not accelerating. And you could say moving with respect to what? Well, here it would be the surface of the Earth that the person's moving with respect to. So you can have either static equilibrium or dynamic equilibrium. And the same could be for rotational motion. You could have something that's not rotating at all, or you could have something that's rotating at a constant speed. So either of those would qualify as equilibria. There are different kinds of equilibria. So this is the idea of balance, and of course we just talked about static versus dynamical equilibrium. Now, the book spends about a page to a page and a half talking about how you treat the signs of forces and torques. And what they're trying to get at, so this is the book discussion in this part. And the gist of it is that you can usually avoid assigning, I'm not going to be able to fit that word there. Let me say it here. Negative signs to forces or torques in solving problems. And the way you do this, I'm going to see if I can get another marker here, because this marker is starting to, yeah, this one's a little better. So the way you do this is if you have a negative sign, you essentially move that quantity over to the other side of the equation. So this is, when I say signs here, you can either write an equation as two forces, so this is in an equilibrium position where the forces cancel, as that one force is equal to the other force, in which case you can use positive signs for both. Or you can say that the one force minus the other force is equal to 0. And this just involves moving something from one side of the equation to the other. Now, we've already seen this, and so this is an example, and we'll look at this static equilibrium situation that I just explained to you. So you have a mass here, and you have, let me actually move it down a little bit so I have room to draw all the vectors. You have a mass here, and you have the force mg, so this is due to gravity. And then you have the normal force, which is mg. So I'm going to write this one as F1. I'm going to call that, I'm going to call this F2 equals mg. Now the way I've written this, I've called the forces the same quantity. I've just drawn the arrows in the different directions. Now you could argue that this isn't quite right, because if I add these two forces together, then I should get 2 mg and the thing should accelerate. So it's just a matter of convention. It's what you choose to call the forces. You know, here what I've done is I've said, okay, in this case, F1, the way I've drawn here, F1 equals F2. The sizes of the two forces are equal, and so they balance. If I wanted to, I could write, and so this is just saying in this case, mg equals mg. If I wanted to write something with a 0 in it instead to say that all the forces cancel, then of course what I would write is F1 minus F2 equals 0. And so in this case, the F1 would have an mg, and the F2 would have a minus mg associated with it. And so I would essentially then be taking the positive direction to go downward and be associating a negative sign with the upward direction here. So, you know, the book suggests that you do try to write equations like this where you try to avoid putting in minus signs. My belief is that there's probably a small group of students, maybe 10% of students, who are on the borderline for problems like this, where choosing to do it one way versus doing it the other way will make a difference whether you get the problem right or not. Most people, either they're going to be able to solve the problem either way, you know, just by reasoning out how the quantities should be arranged, or else they're not going to be able to solve the problem, and worrying about where the signs are is only going to make matters worse. So I'm not going to really give you advice one way or the other. I think you should be thinking about the problems. Either way is acceptable. You know, you can write, and the same will go for torques as well. You can either say there's a positive torque in this direction, or you could say there's a negative torque in this direction, and they mean exactly the same thing in terms of what happens dynamically. So, I don't know. This is one of those cases in which it's maybe easier for you to understand it when you're working problems yourself and you're having to come down and say, should I put a minus sign here or not? So I don't think it's useful for me to discuss it any further in this context. Now, the last thing in this section is a particular equilibrium problem, or a problem that asks you to design something so it will be in equilibrium. And I've drawn kind of a free body diagram here in the sense that it has the necessary quantities in it, but it doesn't have the details. So I'll draw a little bit more detail here. The idea is you have a board. So this is a book problem. So you have this board that goes across this way, and you have a rope. So here's a rope going up like this at some point here, and the distance from the end of this end of the board to the rope here is, we'll call it X. Now the board's going to exert some tension force on the rope is going to exert some tension force on the board, and the tension is going to go up. And then you have over on this side, you've got the little cartoon character they've got in the book, which they call Salty, who's hanging on this end. And so he's a cracker, right? I'm not going to succeed in drawing a cracker. So here's your little, cracker. And so he's hanging on the end over here. And so he's pulling down. And I'm going to call the force here MS, that's for Salty, G. That's the force that he's exerting. He's over on the other end. And then you have the liberty to hang this hippo, and I don't think I'm going to succeed in drawing a hippo very well either. But you have this hippo that's on this, and so this is this big, sort of, you're going to laugh at me for trying to draw this. What does a hippo look like? So it's got a big sort of, I don't know, this is like the worst hippo ever drawn. It's like a cross between a pig and a horse or something. So here's your hippo here. And the hippo exerts a downward force of M, mass of hippo times G. And this distance here is D. You call that distance D. And then the total distance, so this is the total length of the board. It's going to be, so this total length from there to there is going to be called L. And so what you want to do is you want to solve for D to create equilibrium, or achieve equilibrium, let me say it that way. So this is the sort of the mathematical way, or stripping down in terms of the procedural way to say, where do I hang the hippo? This really doesn't look like a hippo. But I guess I could make its ears smaller. That would be one improvement. It still doesn't look like a hippo. But anyway, where do you hang the hippo? What does D have to be? Where do you hang the hippo in order to make the thing balance? Now, I've used up all my space here, so to write equations, I'm going to have to erase stuff. But before I erase stuff, what I'm going to do is I'm going to show you what the choices that are made in the book, and these are decent choices in terms of coordinate system. So I could have this point be 0, so this here is going to be the fulcrum. So this is this end of the board. And then there's going to be 3 torques that are exerted here. So you have the hippo pulling down here. Now this makes the board want to rotate in this direction. So that's one torque. And then I have the tension here, and this exerts a torque in that direction. It makes it wants to rotate that way. And then this exerts a torque in that direction. Now you could ask, why did I choose this to be the fulcrum? It turns out that you're allowed to choose any point on here that you want to be the fulcrum. and you'll still be able to solve it. It just happens to be a convenient choice. Now you could say, well, how do I know that this point doesn't move? Because we're assuming that we're solving for the situation where it's going to be in equilibrium. So I can assume in particular that this point is not going to start moving on me partway through. So I'm going to call this torque, I don't remember if these are the same order in which they have in the book. That's going to be T1, that's going to be a T2, and that's going to be a T3. Now, the way the book would choose to write these, and this comes into this discussion of signs, is the book would say, okay, I have two torques, the T1 and the T3 going this way, clockwise, and I've got one going counterclockwise. So I want to write the equation to avoid putting minus signs in there, and the way I'll do that is I'll say the one that's going counterclockwise is going to equal the sum of the two that are going clockwise. And that's the equation that I'm going to use. Now I'm going to erase, well, I don't know, maybe I have room to work it out down here without erasing this here, so I'll try to do that. Okay, so to begin with, what's T2, since this is over here on the left-hand side of the equation? Well, the rope is pulling up vertically on the board, and so that says that the angle at which this torque is applied is 90 degrees. So what the T2 is going to be is it's just going to be the size. This T here, by the way, this is a force. It's a tension force. And so the size of the T2 is just going to be the size of the tension force times the length of the lever arm for this force. What's the length of the lever arm for this force? It's x. So you write Tx. That's the left-hand side of the equation. This equals, what's T1? Well, the hippo is pulling straight down. The force is mh times g. This looks more like an N than an H, but you know it's supposed to be an H. The force is mh times g. The distance, the lever arm, is d. So you'll have the force, this is mh g d. And then you have the torque that's exerted by the little cracker here. You know, if you actually put numbers into here, the cracker would be like, I don't know, 10 grams or something, and the hippo would be like 2,000 kilograms, and so the distance for D would be almost the same as X. It would have to be really close to there to make the lever arm sufficiently small. But we don't have to substitute in values here. We'll say here, plus, so this is the force, the mass of the cracker times G, and then what's the lever arm here? Well, it's L, because we're taking this to be the fulcrum here. So this here is L. Now, what we wanted to solve for is D. See, solve for D. So the way I could do this is I can write, first I move this part here over to the other side of the equation. So I say Tx minus msgl equals mhgd. See, you know, you're going to get minus signs sometimes anyway, and that's part of the reason why I'm not really giving you advice whether you should avoid minus signs in the beginning or not. You know, sometimes they just show up. And then you're going to divide both sides by this mhg to isolate the d. And so what you'll end up with is that d equals, what does it equal? Well, it's just this algebraic expression, Tx minus msgl over mhg. Now, if you wanted to, you could substitute numbers into there, but I'm not going to do that. The book doesn't do it either. The book doesn't even work as far as getting the expression for it. It says that you can just plug and chug once you get these equations, which you can. So this is the expression that you get. And that will do it for these three sections.